Alright, let's talk about 5.4, right triangle trigonometry. So let's do some right triangle trig here. Let's derive the coordinates for theta equals pi over 4 on the unit circle. And of course, what I mean by that is, let's extend ourselves a line. We'll do the entire thing in blue here. So from the center, I just have quadrant 1 here, and let's get ourselves a nice 45-degree angle. Looks about like that. So there we go. So then this right here is, of course, theta equals pi over 4. And what I want to know is, what are the coordinates here? Now, of course, we know the coordinates are root 2 over 2, root 2 over 2. Because we've done this. We've memorized the unit circle. But where do they actually come from? Where did we get those numbers from in particular? You just believe them because I told you? I hope you don't. So let's see what we can do to figure out the different parts here. So let's take this and let's just drop a height here so that we are perpendicular to the x-axis. So let's drop a height straight down. Drop a height straight down. Something like that. So that this is 90 degrees. And if it doesn't look 90 degrees, it is because I said so. So we start noticing a few things here. At theta equals pi over 4 here, the radius of the unit circle will bisect our first quadrantial angle. That is, our first entire 90 degrees here. We have bisected this. We have cut this in half. Now, the radius then is going to lie along the line y equals x. We know the length of this line already. We know the length of this line right here. This is just the radius of the unit circle. The unit circle goes off the screen, but it has radius, unsurprisingly, 1. So we know the radius of this thing is 1, which means that the hypotenuse of this thing measures 1. So we know a couple other things. We know that this guy down here measures length x, whatever that is. And we know that this green guy over here measures length y. But we know that y equals x. We know that these are the exact same thing because, well, we're in a 45, 45, 90 triangle. That's from right triangle trigonometry. We know that this also equals pi over 4. And in a triangle, your angles must measure to pi radians, or 180 degrees. So we know that x has to equal y. So then we know for a fact that x absolutely must equal our y here. We know that beyond the shadow of a doubt. And we know one other relationship between x, y, and r specifically, and I'm going to do the entire thing here in just blue, but specifically we know that x squared plus y squared has to equal the hypotenuse squared. And we know that the hypotenuse is just 1 squared. But not only that, we also know that x equals y. So instead of writing y, we're just going to write x again. This is x squared plus x squared equals 1. Why are we able to do this? Because x and y are the same. So instead of writing y, I just write x. X squared plus x squared is 2x squared equals 1. Divide by 2, I get that x squared equals 1/2. And then the only step left to do is come up here and say that, take square root of both sides, I get x equals, now it'll be plus or minus, but x is obviously positive here. So we will be dealing with a positive square root of 1 over 2. And that means that x equals the square root of 1 over the square root of 2. And that means that x equals 1 over the square root of 2, which, of course, if we multiply top and bottom by root 2 over root 2, just multiply top and bottom like that, to rationalize the denominator, we get root 2 over 2. Of course, we can do the exact same math and instead replace the x with y and get y squared plus y squared, do the exact same math, and we'll notice that our y also has to be root 2 over 2. Therefore, this coordinate is root 2 over 2, root 2 over 2. So we're just taking a lot of advantage of the fact that x equals y. This is the line x equals y. And if that isn't enough for you, this is a 45, 45, 90 triangle. You know that x has to equal y. The legs have to be the same length because their corresponding angles are the same. And we know that from geometry. So that is for theta equals pi over 4. Now let's take ourselves a look at the next one of these. All right, now let's look at the coordinates for pi over 6 on the unit circle. So pi over 6 is going to look something like, let's do it in green again. It's going to look something like a 30-degree angle. So there's 45. We'll call that 30. So it's going to look something like this. And it's going to work a lot the same way. So we're wanting to find these coordinates here. And of course, we know these coordinates here. They're root 3 over 2, 1/2. We know that. But how did we find that? What was the math behind that? How did we get there? Was it just because I said so? Again, not quite. So it works exactly the same way. We're just going to drop a height here because we need some additional information. So we're just going to drop a height here so that this is 90 degrees. Let's go ahead and mark that. But we're going to go ahead and help ourselves out because this isn't a very useful triangle. We can't use the fact that this is congruent to this because they're not congruent to one another. So what we'll have to do is come down here and do a negative 30-degree triangle as well. Let's say about like that. And then we're going to go ahead and drop ourselves a height as well from here back up to here. And you should notice that it's all part of the same line. So we're also going to drop this at a 45-degree angle, or at a 90-degree angle, rather. So we'll have the construction like this. So this is theta equals 30 degrees this way, or pi over 6 if you prefer. This is theta equals also pi over 6, just in the other direction. And yes, that is negative pi over 6, but in terms of actual rotation, you have rotated pi over 6. So keep that in mind, that these are the exact same thing. And what we've done is we've just copied this top triangle and flipped it over the x-axis to get here as well. As we go through this, we'll notice that all of the angles of this large right triangle, the entire green triangle, are equal. That is, look here. This must also measure pi over 6. We know that this up here has to measure pi over 3, rather. And this up here has to measure pi over 3. And then this right here measures pi over 6 plus pi over 6, which is pi over 3. And if you don't believe me, it's a 30, this is 60, 90 triangle in both of these, and that's what we're wanting to do. So in the large triangle, because all of your angles are equal, then your sides are also equal. Well, we knew the length of this right here was y, and we know the length of this here is y as well. By definition, the length from the x-axis to up here on the unit circle is y, then we know that the entire length is 2y, which means that we know that this is length 2y as well, and we know that this is length 2y as well. And because we know that this was our radius, which was 2y, and we also know that our radius has to be 1 in the unit circle. So it's the exact same math down here. So we get that 2y equals 1, or that y equals 1/2. That's the easier part of that, but that is the y coordinate. And we know that when we come in here and we put in the y coordinate, it's going to be something comma 1/2. Root 3 over 2 in particular is what we should get here. So that's how you got your 1/2. That was easy enough. You just noticed that 2 of these y's was exactly the same as the length of your radius. You got 2y equals 1, and you solved 2y equals 1 to get y equals 1/2. I literally just solved that to get that, is all that I did. So keep that in mind. Now, let's look at some tricky little math in order to get the x-coordinate for this guy in particular. So we know, in particular, that we have a y here, and we know r here. So all that's left to do is to find x is simply the Pythagorean Theorem. And I have this entire place over here. I'm just going to do the Pythagorean Theorem inside here. We know that whatever x is squared plus y squared, so y was 1/2, we know that, squared, has to equal 1 squared. We're just going to solve this for x and we'll be done. Watch this. So x squared plus square the top and the bottom. 1 squared is 1, 2 squared is 4, equals 1. Subtract 1 from both sides. So subtract 1/4 from both sides, rather. So you get x equals, well, 1 was just 4/4 minus 1/4. So you get x squared equals 3/4. Then you take the square root of both sides, and you get x equals the square root of 3/4. You take the positive square root, because it's obviously a positive x that we went out up here in the first quadrant. And then it's the square root of 3 over the square root of 4. So x equals the square root of 3, which is square root of 3, over, and then it's the square root of 4, which is 2. And hey, look, we've got ourselves the square root of 3 over 2. Don't overcomplicate this. That's how you get square root of 3 over 2, comma 1/2 for that particular thing. That obviously only leaves pi over 3. Now, I'm not going to go over pi over 3 in this video, but it is a lot like this proof that I just did here. If you want to convince yourself of how to do pi over 3, you're more than welcome to look in your OpenStax book. There are plenty of tutorials online for it. Or I challenge you, pause the video, and try to see if you can construct something here yourself. We're just using some facts about right triangles that we remember from trigonometry. So just remember, we get root 3 over 2 from this. This was just root 3 over 2, like that. So that's all that there is for this one. Let's look at a couple more things, and then we're done. So given a right triangle with angle theta opposite side A equals 33, hypotenuse C equals 65, and other leg B equals 56, find the 6 trigonometric functions with regard to theta. So here's the one thing that you're going to want to remember is, well, all of this. It's that sine of theta, okay, the cosine of theta is going to be something, the tangent of theta is going to be something. I'm just going to keep writing these down here. And then each of their reciprocals. So cosecant of theta, and this is the normal order that we write these in. The secant of theta, and then the cotangent of theta. And each one of these, in terms of a right triangle, have things. And you'll remember this from geometry. But we used this. So we used opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, and then if you wrote it right, it'll just be these except they're reciprocal. Cosecant will be hypotenuse over opposite, secant will be hypotenuse over adjacent, and cotangent will be adjacent over opposite. You remember the SOHCAHTOA definition of things, the SOHCAHTOA definition of things. That is, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. That's the thing that you remember. And then cosecant, secant, and cotangent in that order. Remember, cosecant and sine are related, secant and cosine are related, cotangent and tangent are related. It's just the same thing, but in reverse. So using that, we can just draw ourselves a picture and figure out what we can learn here. So let's get ourselves a right triangle. So first off, draw the right triangle however you want to. I don't care. I'm just going to draw it like this because I feel like it. So we're going to go straight up and down. We're going to come over here like this. And then I'm going to come up here like this. And this is at a 90-degree angle rather. And we've got angle theta opposite angle 33 degrees. So let's call this our theta right here. You can put it anywhere you want to. So it's opposite side. Okay, so here's A equals 33. That's opposite. Our hypotenuse is 65. Our hypotenuse is 65. And I don't want to put the A equals on there. I just want to put the 33 on there. So 33 on there. 65 was our hypotenuse, and our other leg was apparently 56. Okay, so this triangle isn't to scale, but that's fine. It doesn't need to be from scale. We just want to find the 6 trigonometric functions with regard to theta. Now, I put theta here, and remember, theta is opposite 33. So theta, you go to the other side, it should have 33 on it. And it does, so we're good to go. So go ahead and label these things opposite, adjacent, and hypotenuse. Here's how you do it. Look opposite theta. Just come straight out of this angle in a straight line until you hit the side. That's the side opposite. Go ahead and label it. I'm going to label it in a different color. I'm going to label this O. This is opposite. Okay. The hypotenuse is the same thing with the right angle, which means that the adjacent must be the other side. So there's your three things. So in order to figure out all of these, you just plug in these numbers. So we'll come back over here. Look here. The sine of theta must be opposite over hypotenuse. Must be opposite over hypotenuse. Well, opposite was 33. Hypotenuse was 65. So it must be 33 over 65. Okay? Let's go on to the next one, and I'll do it in blue. So the cosine of theta must be adjacent over hypotenuse. Just write that down. Must be adjacent over hypotenuse. Well, adjacent was 56, so it's 56 over 65. Let's do tangent. Tangent of theta is always opposite over adjacent. Well, opposite was 33. Adjacent was 56. Now, with sine goes cosecant. Cosecant is just sine's reciprocal. So cosecant is just hypotenuse over opposite. So it's 65 over 33. I'll come down here and I'll do cotangent as well since I still have the color. Cotangent theta is just, I'm just going to flip this. It was just adjacent over opposite, or 56 over 33. And then the last one, which is secant, which is the reciprocal of cosine, that is 1 over cosine is secant, is just going to be hypotenuse over adjacent, which is 65 over 56. So set up that way, that's all that there is to it. You just found the 6 trigonometric functions with regard to theta. Now, if you want to simplify these down, if they do indeed simplify down, none of these seem to do that. But if you want to simplify these down, go ahead. I don't believe that your assignment asks you to do that, though. So just keep these in mind, these definitions in mind. And the hardest part of this is honestly just setting up the triangle the way that I did. I could have put theta down here if I wanted to, and if I did, then this would have been 33, and this would have been the side opposite, and this would have been 56, and this would have been the side adjacent. However you want to go about doing it, notice that you don't have to know theta in order to know the angle relationships, or the side relationships rather, of the sides opposite, adjacent, and hypotenuse. That is literally the definition of sine, cosine, tangent, cosecant, secant, and cosecant. And just try and remember this relationship here, this relationship here, and this relationship here, as in they're just reciprocals of one another. That is, 1 over sine is cosecant, 1 over cosine is secant, 1 over tangent is cotangent, or if you want to go the other way, 1 over cotangent is tangent, 1 over secant is cosine, 1 over cosecant is sine. These are all things you're going to have to learn in the future. Anyway, may as well get a head start on it. So let's go over one more little thing, and I'll show you how it works, and it'll be something you'll want to write down, and then we're done with the section. So given an angle theta, we have the following cofunction identities, and each one of these are just minuses. So we have that the cosine of theta equals the sine of pi over 2 minus theta. That the sine of theta equals the cosine of pi over 2 minus theta, and that tangent equals the cotangent of pi over 2 minus theta. This is actually why you have the co in cosine. Cosine is just, well, it's the sine of the other angle, and I'll show you what I mean here in just a second. But take a minute and write all these down, and remember that pi over 2 is alternately just 90 degrees. And we'll remember something very specific about this, because when we're dealing with all of these, remember that we're dealing with right triangles. Remember that we're dealing with right triangles when we're dealing with these. And I'll show you what we mean. We can go ahead and read example 4. It says, show the derivation of the cofunction identities for sine and cosine using a right triangle. And the rest of them follow from the fact that we can define cosine and sine this way, because remember, tangent, cotangent, cosecant, and secant are all just different forms of sine and cosine. So let's look at example 4 here. So let's look at example 4 here. It says, let's go ahead and show the derivation. So we want to use a right triangle, and I'm just going to put up a very large right triangle here. So here we go with a right triangle. Good enough. Good enough. And then let's connect these two ends to each other for the hypotenuse. Okay, and it's a right triangle. So even if it wasn't a right triangle before, it is now because I said so. And I need to put theta somewhere. I need to put theta somewhere. So I'm going to choose to put it down here. But I could have put it up in the other part if I wanted to. So the thing that we need to know, is now, this is the side opposite, this is the side adjacent, and this is the hypotenuse relative to our theta. But we also need to know what is the measure of this angle up here. What is the measure of that angle? Well, we know that the three interior angles of a triangle need to sum to 180 degrees. We know that 90 degrees of it is already taken up right here. So we know then that these two angles, these guys right here, need to sum to 90 degrees, whatever they are. So we know then, for just a moment, let's just call this, I don't know, theta prime. So we know that theta plus theta prime need to equal 90 degrees. Or we know that theta plus theta prime needs to equal pi radians, because 90 degrees is pi radians. Then we know that theta prime, which is what we're trying to solve for, theta prime has to be equal to pi minus theta. So theta prime is just pi minus theta. I just subtracted the theta over. I'm just trying to solve for theta prime. So then we know that this angle up here is just pi minus theta. So I'm going to get rid of all of this writing, and I'm just going to go ahead and write that up there instead. We know that this is just pi minus theta, this angle here. Whatever theta is, this is the 90 degrees minus whatever that was. Okay, now let's use sine and cosine. So sine, look here, sine of theta is, by definition, opposite over hypotenuse. Okay? Now, let's take a look at cosine of this other angle. Cosine of pi minus theta, which is its own angle. The cosine of pi minus theta, okay, is the side adjacent to this angle, which is this guy right here. It's the guy adjacent to this angle, which is opposite, which is what we call O, over hypotenuse. So notice how these are the same thing. Therefore, we can say that sine of theta equals the cosine of pi minus theta. Remember, when you find the cosine of theta minus pi, we're talking about this angle right here. The cosine is always the side adjacent over the hypotenuse. The side adjacent to that angle is this side. It doesn't matter that it's called O. It just matters that it's the adjacent side. It happens to be called O. So it's the same side as what it was for sine actually being opposite. They are the same thing. That is, they are cofunctions. You may imagine, and I'll do it over here in orange, that there is the exact same argument for cosine. But watch this. The cosine of just normal theta is, by definition, adjacent over hypotenuse. But then the sine of that new angle, pi minus theta, well, the sine of pi minus theta, the sine of this, is always going to be the side opposite it, which is this side right here, which must be A, over the hypotenuse. And you notice that these are the exact same things too. So we can say, therefore, the cosine of theta equals the sine of pi minus theta. And we know that those work out. If you would like to find the rest of the cofunction identities, turn everything into sine and cosine, and you're done. And we're done. That's the end of this. So keep in mind the cofunction identities. They'll come in handy in the future, and they're the first of many, many identities that we have. But that's all for 5.4, and we'll hop into Chapter 6 next video.